Hi, everyone. Thanks for coming. Today, we are going to talk about our work on understanding the dimensionality of word embeddings. And at the end, we might talk about something about the application of it. So in the modern era of deep learning, embedding methods has become a universal tool. It turns discrete tokens like words into Euclidean space. These vectors can then be used to discover relationships, various relationships between words like word relatedness and analogy. Moreover, this can be fed into a deep neural network to perform more sophisticated analysis. So today we are going to talk about dimensionality. So although word embeddings play such an important role in modern deep learning era, there has not yet been enough understanding about them. So today we are going to tackle from the dimensionality of word embeddings. It specifically impacts the training and inference time, as well as the performance of your algorithms. So empirically, people have empirically discovered that there is an optimal dimensionality for word embedding. So this is a plot by Professor Sanjeev Arora. So the vertical axis is the horizontal axis is the number of dimensionalities, and the vertical axis is the proportion, the correlation text of the word embeddings constructed from various dimensions, and with the human label test. And as we can see from this plot, that there's a sweet spot here. So here, the higher the correlation, which means the closer the word embeddings is able to encapsulate the meaning of the words. So our study is motivated by this sweet spot phenomenon. So as we've seen from the previous plot, the training, inference, and storage are either linear or quadratic with respect to dimensionality. So this is because in real-life tasks, the number of parameters for embedding is a linear function of k, and the number of parameters if you're using neural networks is a quadratic function of the number of the dimensionality k. So what do we do in practice? So it is either, usually people do this by just choosing maybe their favorite number, like 300, 400. That's maybe because the first paper on like word embedding used that dimensionality. Or what's more common in practice is that we do a gray search. We train a handful of models with different dimensionality and select the one with the best empirical performance. Hence, we need a rigorous and theoretically justified dimensionality selection procedure. So here are the main contributions of our talk. So in this paper, we develop a mathematical framework that quantifies the effect of dimensionality on embeddings. We first aim to explain the sweet spot phenomenon using from a theoretical point of view, rather than like instead of just attributing it to underfitting and to an overfitting. We're also going to establish dimensionality selection procedures for most of the word embedding algorithms. I would say like most context-free word embedding algorithms that are very popular in the academia. So we are also going to quantify the robustness of those algorithms with respect to overfitting. So our main object is an embedding matrix. So we have so in this embedding matrix, we have n rows representing n words. And so this embedding matrix is of dimension n multiplied by k. So k is the dimensionality of the embedding, and n is the number of words in the corpus. It is obtained by stacking the n vectors. Maybe you can continue. Yeah. So maybe I will hand over to you two.
All right, so I'm going to introduce how we select the dimensionality for many popular word embedding algorithms like GLOVE, Word2Vec, or latent semantic analysis. Before going to that, I'm going to first introduce a little bit about the intuition of our framework. So what is the intuition here? We can regard dimensionality selection as a hyperparameter tuning problem. And this hyperparameter tuning problem has been actually very well studied in statistics. Like the way people approach this problem in statistics is they first define a loss function. Think of like a parameter estimation problem. We have an unknown parameter theta star, and we want to estimate a theta star using an estimator called theta hat. And the way people usually do this is to first come with a loss function between theta star and theta hat. And we minimize this loss function in order to obtain an estimator. And we want to do the same for word embeddings here. So two important notions for word embedding. One is called the oracle embedding, which is the theta star, the optimal parameter in statistic analysis. And we also have E hat, which is the training embedding, where we obtain from training a specific procedure on a corpus. And we call it the train embedding. And if we want to apply this same statistical procedure, we need to fill in all the missing steps. First, if we have an oracle embedding and if we have a train embedding, we need a proper loss function between them to measure their closeness. And we propose this loss function called p-loss, pairwise inner product, which I will introduce shortly. And after we have this loss function between word embeddings, we can express this loss function as a function of the dimensionality so that we can select the dimensionality k that minimizes this loss function. And that is the procedure for our dimensionality selection proposal.
So I think before we proceed, I want to ask if there's any questions about the setting of our.
Yes.
Is E a statistic, or is E the embedding function that you're learning?
So E is the embedding function we want to learn, the unobserved, like AKA optimal embedding. But because like this thing is unobserved, when we're actually carrying out the training procedure, we're giving the procedure a corpus where we estimate some quantities from corpus, like word co-occurrence probabilities. And the embedding is obtained by working on the estimated co-occurrence probabilities, and that is E hat. So our goal here is to want to minimize the distance between E hat and E in order to find an optimal train embedding. And there is a handle we can tune, which is K, the dimensionality. And we want to find the optimal like dimensionality. We want to tune that knob to minimize the distance between E hat and E. So essentially, there are two things missing here. One is there is no proper loss function between word embeddings. And that's like our first contribution. We proposed the pairwise inner product, or the p-loss. And secondly, we were able to express this loss between oracle and training embedding as an explicit bias variance decomposition so that we can find a balance that achieve balance between bias and variance.
And I also want to make the point that this oracle embedding is specific to a word embedding algorithm P that the original embedding algorithm is aimed to achieve. So please feel free to ask if there's any other questions, and then we can proceed.
I will go to that shortly. Yes. So before answering Emma's question, let me first introduce like what is the loss function we are working with. This is a question we want to answer. Suppose we have two embeddings, E1 and E2, where remember E1 and E2 are two matrices. How do we measure their closeness, right? And the naive answer people might think of is probably just do like a matrix distance comparison. We have two matrices, E1 and E2. We take a difference between E1 and E2, and we take the Frobenius norm. And that is undesirable because word embeddings are essentially unitary invariant. It means that if we have a embedding E1, and we rotate the embedding for like 180 degrees, The one after rotation is essentially identical, but if we compare the difference between the one before and after the rotation, the difference will be large, and this is undesirable because we are assigning a large distance to essentially the same object. And we are proposing a loss function to deal with this phenomena. And here is our proposal. Suppose we have embeddings E1 and E2. What we're doing is we take an outer product between E1 and itself. So we get E1, E1 transpose. And we do the same for E2. We get E2, E2 transpose. And then we take a difference between the outer product, and we take the Frobenius norm. So instead of taking the Frobenius norm directly between the difference of the original matrices, we take the difference between their outer products. And why does this make sense? This, like at a first glance, is not clear why this is a proper loss function between word embeddings. Now, if we look at the ij's entry of this difference between outer products, the ij's entry between E1, E1 transpose and E2, E2 transpose, it is the difference between the inner product of the vector embedding for the ith word, Vi, and the embedding for jth word, Vj. So we take the inner product and we compare how different the inner product is. And we take a summation over all the inner product between the vector embedding pairs. And we call this the pairwise inner product loss. And that's the expression for the loss function. And what is the intuition here? We say that the pairwise inner product, or P loss, it measures the shift of vectors in the two embeddings. And this measurement is taken under an invariant coordinate system. And because of this invariant coordinate system, we remove the dependency on the vectors on their specific coordinate system. So it will be invariant under unitary transformations like a rotation or reflection. So why is it the case? Why do we call it a invariant coordinate system? Now let's look at the ith row of E1, E1 transpose minus E2, E2 transpose. So this is essentially like, this is the ith row here. It's the inner product between the ith vector Vi with all other vectors V1 to Vn for like all the words in your vocabulary. And it is essentially establishing a coordinate system of Vi using every other word as anchors. Like we first measure the inner product between Vi and V1, and that's the first entry in the vector. And we do that for every pair of words. So we're essentially measuring the location of Vi against all other vectors here. And for the second embedding, we are doing the same. We measure the ith vector against every other vector using them as anchors. And now when we take the difference between these two n-dimensional vectors, we're essentially measuring the relative shift of Vi. And like the shift is relative to all other vectors. And so when we measure the relative shift, this measurement will be independent of your unitary invariance, like unitary operations on the embedding. Like if you rotate E1 by 180 degrees, this relative position will still remain the same. So it makes the measurement robust to such operations. Yes?
Yeah. So is it possible if you can do a global alignment of two sets?
Yes.
Possible to have other loss function corresponding.
So like another way is if we have like E1 and E2, right? What we can propose a loss function to be something like E1 minus E2 times Q, where this Q is like a unitary matrix. That is also something we can propose.
Yep.
And actually in a separate paper, also like in NIPS this year, we proved that these two quantities are equivalent. So essentially, our argument, if you call this quantity A, and if you call our quantity B. And you can prove that we have this inequality. So if you regard both like this one and this one as like metrics, they're essentially equivalent metric. And we also demonstrate that like our metric here, like this quantity, is better because you can actually use it to compare vectors of different dimensionality. Like if you have a 200 embedding here, if you have 300 embedding here, this quantity still makes sense. But now you can do like operation, like mapping, yeah. Yes, and you don't need to do like optimization, right? Like that is a pretty nasty optimization problem.
So this PIP method, out of this context,
Yes.
has it been applied to like deep learning loss functions? Because I don't think I've seen
No.
applying. Yeah, because so what other other than this specific word embedding, has PIP been used elsewhere?
No, this is the one we proposed. So I don't see like this loss function being proposed or like applied at other places. This is specifically appropriate for word embedding because this loss function is it has a property that is unitary invariant, and we want to know like at what locations do we want this property, and word embedding is like one of them. And if in deep learning or any other fields, if there are particular situations where unitary invariance is needed, then this loss function might be applicable. Yes, probably, yeah. And this measurement is purely on the geometry of word embeddings. It doesn't take consideration into like how do we want to use the embeddings. And one one argument people may have is like I don't care about the theory, right? I don't care about how you measure or interpret their geometric properties. What I care about is how can I use word embeddings in practice to solve problems like, for example, word relatedness or word analogy. And word relatedness and word analogy are essentially the most fundamental practical applications of word embedding, specifically like before people using contextual or like neural network embeddings. Word relatedness is measuring the similarity between words. So like here we see like car and bus, they're more similar, so they get a score of 0.8. The score is like is between 0 and 1, and the higher the score is, the more similar the words are. So car and bus are more similar, but car and drink is like not that similar. And people can actually discover these word similarity relations by looking at the cosine distance, cosine similarity between the vectors for the words. And also we have this notion of analogy, where we have two pairs of words, and we want to see if the relation between the two pairs of words are the same or not. And this can also be discovered using word embedding by taking the difference between the two pairs of vectors and see if they are roughly pointing towards the same direction in the space. Here are two pictures. First is relatedness. We look at all the vectors and we find their cosine angle between the vectors. And a larger cosine means that they are more similar. And also this one is like, I guess people have seen this already, like the analogy figure where all the difference between word pairs are pointing towards the same direction in the space. And why does this also relate to the pairwise inner product loss? And the argument is essentially that both relatedness and analogy, when we're using word vectors to discover them, we are measuring something that is highly related to inner products. Like word similarity is the inner product, and we normalize it by their like length of the vectors. And analogy is taking the difference between vector pair. And we can also prove that this is controlled by the inner products between all vector pairs. So the conclusion here is that if we have two embeddings, E1 and E2, and if we have two embeddings, E1 and E2, and their p-loss is small, and then all the relatedness and the analogy relations between the words are similar. And we are also to prove the other direction, meaning that if we have two embeddings and all the words in the all the words in the two embeddings, they have similar relatedness or analogy relation, then the p-loss between the two embeddings are small. So the conclusion is that the p-loss not only give us a geometric characterization of word embedding, it also controls the practical applications, practical quantities we care about when we use the word embedding. And the reason is because these relations are actually reflecting some of the geometric properties of the word embedding. For example, the angles between the vectors, or the whether the vector differences are parallel to each other. They are essentially geometric properties. So they are like partial reflection of the p-loss. And yes, that's essentially our theorem. We prove that if the p-loss between two embeddings are small, then their relatedness and analogy relations are close to each other, and vice versa. So now we have an answer to the first question. That is, how do we define a loss function between word embeddings? And the answer we give here is the p-loss. And now what we want to do is use this p-loss to do something like dimensionality selection. Our goal here is to express the p-loss between the oracle embedding E and the training embedding E hat as a function of k, where the k is the dimensionality of the training embedding E hat, the knob that we can tune. And if we are able to do so, then we can tune that knob to find the embedding that actually minimizes this loss. So before going to the detail, let me first introduce what is E and what is E hat. So people have discovered that many embedding algorithms are essentially doing matrix factorization. For example, there is a recent paper in 2014. They proved that the famous word-to-vec algorithm is doing an implicit matrix factorization on the point-wise mutual information, or PMI matrix. And also in the original glove paper, when the authors proposed the glove method, they explicitly saying that the glove is doing a factorization on the log count matrix. And so under this observation, we found that if an embedding algorithm can be formulated as a matrix factorization, then we can actually express the p-loss as a function of the dimensionality. And I don't know why I'm missing a slide here. So I'll just describe the E and E hat here. So remember that the embedding algorithm is doing a matrix factorization. First, we have a matrix M. So let's use word2vec as the example. The matrix we want to factorize is M, which is the PMI matrix, pairwise mutual information, pointwise mutual information. And Mij equals log of Pij over log of Pi times log of Pj. So these are all the entries in the matrix, where Pij is the co-occurrence probability between word I and word j. And Pi is the probability of occurrence of word I, and Pj is the probability of occurrence of word j. And an embedding can be obtained by doing an SVD on M. So we get U, D, and V transpose. And the embedding matrix is U times D to the alpha, where we truncated at a certain dimension K. And this gives us a K-dimensional embedding. And so what is the oracle embedding and what is the training embedding here? Notice that this Pij, Pn, and Pj, they are unobserved. They are the inherent co-occurrence or occurrence probabilities of between the words, which is native to a language we don't observe. But when we're doing the actual training, we don't observe this m, but we observe m tilde, which is log Pij hat over log Pi hat log Pj hat. And these Pij and Pipj, they are estimated by counting the co-occurrence frequencies in the corpus. Yes. No.
It's not the determined vector that you find for that word in the word embedding. And if you say co-occurrence, are you just looking at counts of the word and between two words?
Yes. So we have a context window of, say, like 5. And the co-occurrence probability is how often two words like I and J appear in the same context window. Yes. So we don't observe Pij, but when we have a corpus, we can estimate Pij by actually counting them. And so this actually gives us estimation noise, where we characterize as m plus z. So this m here is the original matrix. But since we are doing estimation on the corpus, we have additional estimation noise, where we call z. And so the oracle matrix is obtained by doing factorization on this clean matrix M. And our trained embedding, where we call E hat, is obtained by doing factorization on the noisy embedding, where M tilde equals SVD. Sorry, let me do this. Where U tilde, D tilde, and V tilde are from SVD of M tilde. This is what we do when we're actually doing the training. Yes.
Is the SVD factorization dimension the same as your K, or is it another parameter?
Okay. So K here is the dimension of this E hat. It's essentially where do we want to truncate this SVD.
Which is the same as the dimensionality we are searching for?
Correct. Yes. Yes. So we want to find a K. Essentially, we want to find. So we have an option to truncate at any.
Hi Z, I think we can use the slides. You don't need to write it on the board.
Okay. Cool.
So it's more clear.
Yes. So alpha is another hyperparameter that's specific to your procedure. And for Word2Vec and Glove, the alpha here, you can think of them as 0.5, so you don't need to choose them. But to make it more generic, I just leave it as like an alpha. Like it's a number between 0 and 1. Right. So we have the definition for oracle embedding and trained embedding. And that's the same, yeah. So like here, it's an example where if we use the co-occurrence probability to do the embedding training procedure, we have this oracle embedding that's obtained from factorizing the actual co-occurrence matrix. And we're doing training, we're doing factorization on the estimated co-occurrence matrix. And as a remark, we want the pip loss between E hat and E to be small in order for E to be like a good embedding. It should be close to the original embedding we are trying to estimate here. And that's where we need to use this pip loss, because that's a loss function that measures distance between E and E hat.
So is there any questions so far?
Yes. So before you train the embedding, you have to specify like at which dimensionality you want your embedding to be. Like it's a hyperparameter that's going to your training procedure. Yes. Exactly. Like the loss function doesn't care whether you're doing dimensionality selection or not. We specifically focus on dimensionality selection because the pip loss, like the loss itself, can be expressed as a function of dimensionality so that we can actually do the selection. If you have another hyperparameter that you want to select using the same loss function, then it is not clear whether the loss function can be cleanly expressed as a parameter, as a function of the parameter you want to select. And if you are able to do it, then I believe that you can also use the same method to select like whatever hyperparameter you want to look at. Yes.
My question is, okay, so for here, you assume the embedding are fixed, so every word has a new vector.
Yes.
But if you look at it, like, let's say for false methods like Elmo, the word embeddings depend on the context.
Yes.
So every word, if they appear in different context, have different word embedding.
Yes.
So how do you apply this dimensionality search methods to that?
So the procedure we propose here does not address like any context-dependent embedding like BERT or Elmo. The reason is for our method to work, we need to have a assumption that the embedding are from implicit or explicit matrix factorizations. And for BERT, it's not clear because it's from a neural network, or like Elmo, it's from a neural network. And in my opinion, it is very hard to determine the optimal dimensionality or any other hyperparameter there. The reason is because we don't really understand how neural networks work. And that's a prerequisite to be able to do any parameter selection. And the reason we can do it here is we understand what a matrix factorization does. So we can use our understanding of that like algebraic procedure to do dimensionality selection. And that's why you see like a theorem here. You never see theorems in any neural networks work. Yes.
At this point, is the oracle E is already considered as known, or
It's considered as unknown.
it's still considered as known?
Yes.
From that equation you given, it seems if you have all the word analysis and what are the particular
Yes.
occurrence, you could have that number, right?
You don't because you're still estimating that, right?
So you have
When you have a corpus, you get M tilde, but not M. Because you're doing the parameter estimation, and you will always have estimation noise, unless you have like an infinite long corpus. And that's actually what we discover. As your corpus gets larger, the actual dimensionality, like the optimal dimensionality you can select, also grows larger. And if you think about this intuitively, like the reason is simple, right? When you have a larger corpus, you have lower estimation noise. And so that shifts the optimal dimensionality to the right on your signal to noise trade-off like curve. So that allows you to pick a larger dimensionality without having a risk of like overfitting the noise. And that's like, actually we verified that by experiment. And okay, so let's just quickly look into the theorem. The theorem here says if we have this oracle embedding and training embedding as we set up before, then the pip loss between them, like the expected pip loss, where the expectation is taken on the noise, like Z here. If we measure like essentially the average pip loss between the oracle embedding and the training embedding, it has a bias variance decomposition. Like the first part is a bias, and the second two terms are two variance terms. And I believe I have a figure to explain what they are, yes. So suppose the spectrum of the original matrix M, the M here, it has rank D. So we have a spectrum of the original matrix. And if our training embedding is of dimensionality k, then we are only capturing the spectrum before k. And we're discarding like everything from k plus 1 to d. And that is the amount of signal we lose by choosing a k-dimensional embedding. And that's like the first term here is a term in red. We can actually see that it is explicitly characterizing the amount of signal we are losing because we are summing over the spectrum of the matrix M from k plus 1 to d. And this term gets smaller if k gets larger. If we have a larger k, then we have more of a signal. So we have a smaller bias. And what is the second term? The second term is the variance on the magnitude of the signal. And the magnitude of the signal is given by, so like for the training embedding, it has two parts. Like one is U and the other is D. Remember, there are two quantities from SVD. Like the first part is the direction of the singular vectors. And the second part is their magnitudes. And this quantity here measures the variance on this magnitude part, like the singular values. So in this figure, the blue bars are the original spectrum, the spectrum for M. And the blue plus, like this little orange part, is the spectrum for M tilde. So it's the original signal plus like noise. And now if we increase the dimensionality k, we're including more of the little orange bars. That means we include more variance on the signal direction, and that actually is going to make the peep loss larger. And remember, there's also like a third term in the expression, and that is the variance on the directions of the signal, which is on the first term, the U term, the singular vectors. So suppose we have a small dimensionality for our training embedding. Then we only have like a small set of signals. So like these, the dashed ones are the singular vectors for the training embedding, and the like these arrows, the solid arrows are the singular vectors for the original embedding. And because of the existence of noise, they are slightly different. And if we have a larger dimensionality, we include more of these singular vectors. So the discrepancy between the singular vectors are more significant. And because of this bias variance decomposition of the peep loss, we're able to like actually explain the sweet spot phenomena that are discovered empirically by other people, as you have seen at the beginning of the talk. When we have a dimensionality that's too small, we have a high bias. And we have a dimensionality that's too large, we have like a high variance. And so there is a one that achieves the balance between them, and that is the one we're looking for. And so because of this, we are able to perform a dimensionality selection procedure by minimizing this peep loss. And that actual minimization is by looking for the dimensionality that achieves the bias variance trade-off.
So I think essentially it boils our question down to the estimation of the spectrum, because in our theorem, the lambda and the sigmas, they're essentially so part of the original signal matrix M. Right.
Yes.
M is in a limit as large in dimension as your vocabulary.
Yes.
Do you have a real corpus that you actually apply this?
Yes.
Yeah, we will talk about. Yeah, we can just skip
Yeah, I
the
think I'll
estimation
skip the part.
procedure. But the takeaway from the theorem is like we can, as long as we have a pretty good estimate of those like lambda and sigmas, then we can choose the optimal dimensionality. So.
So for, yeah. If you consider the estimation noise of the actual occurrence probability, that's probably not going to be a Gaussian distribution, because different words has different probability of occurrence. But most of the embedding algorithms, they are not operating on the original co-occurrence matrix. They are operating on like the logarithm of the original matrix, or the matrix that's normalized by their frequency of appearance. In that case, if we have a reasonable number of observations, then like the Gaussian assumption is actually not that bad an assumption, because when we're doing this frequency counting, by central limit theorem, it's going to approach something like a Gaussian. And yes, yes. Like when we are training embeddings, we are actually not training embedding for every word in the corpus. The usual procedure is when the frequency of a word goes below a threshold, people map that to a special token called unknown. So that gives you a guarantee that we will not estimate the probability for the things that we actually can't do. The one in the matrix Z. Well, if you regard the estimation as just as estimation noise, then I think that's a reasonable assumption, because the estimation noise are not like related between each other. I think for pairwise, it depends on like what pairs are you talking about. If you have two pairs ij and kl, then I don't think they're that related, because they are two different pairs. Because but if you have like ij and ik, then there might be some correlations in there. But I think overall that correlation is still going to be small, because if word like j and word k, they are not that the same, then still the co-occurrence probability should be quite different, because they're not going to very likely occur in the same context. Yes. Yes. Yeah, we did a comparison. I did a comparison for the embeddings obtained from GloVe and Word2Vec, and I found that I used like another metric called a normalized p-plus. Suppose we have embedding from GloVe and embedding from Word2Vec. Let's say GloVe is E1 and Word2Vec is E2. This is the original p-plus, and I normalize it by E1 transpose times like E2 transpose. And this quantity is about 0.3. And if, so this is statistically significant. Like the null hypothesis is that E1 and E2, they are completely different. They are completely random. In that case, you would expect this to be something like square root over 2, which is like 1.4. And so I think this is a very interesting conclusion, which essentially says, although GloVe and Word2Vec, they seemingly like very different algorithms. And if you compare their embedding, you cannot tell like how similar they are. But when you apply this p-plus as a metric, you will find that they are actually producing something that are actually statistically significant, that they are closer to each other. So this is not part of our paper, but I think this is like pretty interesting discovery. Yeah, so we have proposed like a theoretical procedure to select dimensionality, and now we want to prove that this actually works in practice. And the way we prove this is we first do a dimensionality selection using our procedure, and then we actually train like these embeddings of various dimensionality, and we evaluate their performance on like a human label data set, like word similarity or word relatedness. And we want to see if the dimensionality chosen by us and the dimensionality chosen by the empirical evaluations are closer to each other, whether they agree or not. And we did experiments for GLOF, Word2Vec, and LSA, so 3 very popular embedding algorithms. I'm just going to quickly show the results. This is for GLOF, like the figure on the left is the pip loss and the bias variance decomposition. Like this one minimizes it, and that's a number you see like in this table. And here it's the actual performance on a word similarity test. Like the y-axis is the correlation between the cosine similarity of a word pair versus like human label, and we want like that correlation to be high. So here, by looking at the highest correlation, we also find a dimensionality. That's produced by the empirical approach, which we see like here. And for every algorithm we cross-validated, these numbers are very close to each other. So this is for GLOF. It's same procedure and same conclusion.
Word similarity of labels across a supervised test?
Yes.
Supervised data?
Yes. Like there is a supervised data where there are human judges like judging word pairs like car and bus. They give you like 0.8 or something like that. Yes. Yes.
You compared how close it is for optimality with the word similarity. How about the analogy?
Yes, we did that in the paper as well. So they are all close to each other, but it also matters on how you define closeness. Like 2 dimensionalities can be far away from each other, but they can have similar performance if your performance curve, if the curvature of your performance curve is like small. Like here for the curve dimensionality 500 and 1000, they actually give you a similar performance. So we also measured the difference between performance, and that is very close for like dimensionality selected by similarity or analogy or like our procedure. So I think that's like the all of our talk. Like essentially, what we're doing is we give like a theoretical understanding of word embedding by looking at their geometric properties and propose a loss function on their geometric properties. And we're also able to use this theoretical framework to do like practical applications like dimensionality selection. And I do have a GitHub repo that like implement this algorithm. And how do I do this? So how do I quit the full screen? All right, it's here. So I want to say that this is a very easy to use program. There are only 3 parameters you need to feed into this algorithm. Like you give it a data set, and you give it an algorithm that you want to select dimensionality for. Like here you say algorithm is Word2Vec. And you give it like a configuration file. Basically this says like what is the context window or some other hyperparameters. And after running this algorithm, it's just going to spit out a number like 200 or 300, which is the dimensionality you want to use when you actually train the embedding. So I encourage you to try this out. Yes.
Would you say something about the performance and computational aspect?
So the computation here, like the most heavy lifting is done on the matrix factorization, like the SVD part when we estimate the spectrum of the matrix. So the complexity grows like linearly with the size of your corpus. So that's like good. And what is not that good is it grows like quadratically with the size of your vocabulary. And so now if you run this algorithm on a vocabulary of like 20,000 words, that's like completely fine. But if you run it on like 100,000, then it's going to be pretty slow, unless you have like a machine with a very strong like CPU and memory. But I think for most of the cases, like vocabulary size between like 20K to like 30K is like reasonable, unless we have like a really, really large corpus.
Just like
Sorry?
But in reality, we have billions of words.
We
in
have
our
billions
corpus.
of words, but we don't obtain embedding for every one of them, because most of the words, they don't occur that often to pass the threshold that we're actually doing the embedding. So many of them are mapped to an unknown token. And also, another thing is people are currently like using a lot of these like subword embeddings, like BPE. And in that case, the number of BPE tokens are usually limited to like a few tens of thousands, like a fast text, if you think of algorithms of that kind. And using like embedding for a very large vocabulary, in my opinion, is not that efficient procedure, because there are fundamental limits. If a word occurs very infrequently, then fundamentally, there's no way you can estimate its embedding, because you don't know enough statistic like properties for that word.
So if you go to your presentation, when you're showing the numbers,
Mm-hmm.
I didn't quite understand. So you had like a glove and the word to
Yes.
vec. So when I see the suboptimality of 0.4 on glove compared to the word to vec, which was 0.7,
Yes.
can you just kind of elaborate more on what those numbers are? Because like those numbers
Yes.
stick to me, and then
Yes.
saying, okay, well, then does it mean that actually glove word embedding
Yes.
is
So you see like two numbers here, like this one and this one. This 800 is the one that achieves optimal on this curve. And suboptimality means if we take this number and we find where it is, like it's like here. And we compare like how much worse of the performance when we select this this dimensionality. Like if we call this curve like f, we have f of a60, which is like the highest. And we also have like f of 177719. And we take like 1 minus them. Yes. Sorry. That's like one way we define the suboptimality when we're using this similarity test. When you use like a different test, it can be different. But also when you have a different test, this number can be different. And that also can be confusing, because if you're using this empirical procedure to select dimensionality, the two tests you work on may not agree with each other, and in that case, you don't know what to do. But if you use like this method, it will give you like a number. And still, the reason is because different tests look at different geometric properties of word embedding. Like this is a cosine similarity, and like analogy is like how parallel they are. But this one looks like looks into like a more holistic view of the geometry of the word embeddings.